So we are going to discuss first mean value theorem, Rolle's theorem. What actually Rolle's theorem describes, first we will see statement of Rolle's theorem. Let f of x is a function such that it is continuous in closed interval a comma b. It is derivable in open interval a comma b. F of a equal to f of b. F of a equal to f of b. Then there exists C in open interval a comma b such that f dash of c equal to 0. This is Rolle's theorem statement. What Rolle's theorem says? Rolle's theorem describes about a function which is continuous in closed interval a comma b and derivable in open interval a comma b, and f of a and f of b are equal. Then there exists one point in between a comma b such that if you substitute that point in its derivative, that should be equal to 0. So that means if you want to check a Rolle's theorem for the given function, you have to check that is continuous in closed interval a comma b or not, and derivable in open interval a comma b or not, f of a equal to f of b or not. If it satisfies these three conditions, then you can check this condition whether there exists c in open interval a comma b for f dash of c equal to 0 or not. For example, we will discuss with one example so that you can understand. Here there is a problem like this. Verify Rolle's theorem for the following functions in the given intervals. For the following functions in sighted interval, in set interval. The first one f of x equal to tan x in 0, 5. So now I am going to test whether we can apply Rolle's theorem for this function. For that, you need to check whether f is continuous in given interval, f is derivable or not, f of a equal to f of b or not. You all know that tan x in 0 to pi, tan pi by 2 value you know, infinity. That means at x equal to pi by 2, you are not getting a finite value, you are getting infinity, which is not defined. That means f of x is not continuous. F of x is not continuous at x equal to pi by 2. Why you know? Tan pi by 2 infinity. That means f does not satisfy first condition of Rolle's theorem. F fails to satisfy condition 1 of Rolle's theorem. Therefore, we cannot apply Rolle's theorem for the f of x. We cannot apply Rolle's theorem for given function. Next, coming to the second problem. This is first one. Second one is f of x equal to 1 by x square in minus 1, 1. Now see, in this interval, you are having 0 also. Minus 1, 0, 1. If you substitute 0 in the place of x, what you will get? 1 by 0. 1 by 0 does not define. 1 by 0 is infinity. What it means? At x equal to 0, f of x has no finite value. That means it has infinity. That means at x equal to 0, f of x is discontinuous. This is the technique which you need to remember. This is a shortcut. Wherever you get infinity, that function is discontinuous. Simply. That is one small technique without using actual formula. So at x equal to 0, f of x is discontinuous. Therefore, again, we cannot apply Rolle's theorem. We cannot apply Rolle's theorem for given function in given interval. Coming to the next one, f of x equal to x cube in closed interval 1, 3. F of x equal to x cube. So here just now I said that 4 important properties which you need to remember, x cube, x power positive integer, which is a polynomial. What I said, all polynomials are continuous and derivable. If you want, you can check here, f of x equal to x cube. If you write in the place of x1, 1 cube you will get. 2, 2 cube. 3, 3 cube. Any value in between 1 and 3, you cannot get infinite value. What it means? F is polynomial. So clearly one can understand f is continuous. F is continuous in closed interval 1, 3. Second one, f is derivable in open interval 1, 3. Next, what is the condition we need to check, Third condition we need to check. What is that? F of a equal to f of b or not. Here a is 1, b is 3. That means f of 1 equal to 1 cube you need to find out. F of 3 equal to 3 cube you need to find out, that is 27. Now these two are not equal. F of 1 not equal to f of 3. So what we can decide now? F fails to satisfy third condition of Rolle's theorem. F fails to satisfy third condition of Rolle's theorem. Therefore, we cannot apply Rolle's theorem. We cannot apply Rolle's theorem for the given function. Rolle's theorem. So when we can apply Rolle's theorem for the given function? Whenever it satisfies these 3 conditions only. If the given function satisfies these 3 conditions, then only we can apply Rolle's theorem. That we will discuss in the next problem, where function satisfies 3 conditions. Okay. So now the next problem, verify Rolle's theorem for the function f of x equal to sin x by e power x or sin x into e power minus x in 0, pi. So the given function I am writing like this, e power minus x into sin x or sin x into e power minus x. So this is the function given. Now we need to check whether we can apply Rolle's theorem for this function or not. For that you need to verify 3 conditions. Condition 1 you know, Condition 1. Condition 1 is whether the function is continuous or not. Clearly we know that sin x is always continuous. I said 4 points, 4 most important points. If you remember that one, you can easily identify the function is continuous or not. I said the trigonometric function sin x and cos x are always continuous. No need to check. Similarly, the exponential function e power minus x is also always continuous. That means the product of 2 continuous function is continuous. That means e power minus x into sin x also continuous. E power minus x into sin x also derivable. That I had given already. So here, basing on that point, you can easily say, clearly f is continuous in closed interval 0, pi. Next, f is derivable in open interval 0, pi. So 2 conditions over. Coming to the third condition. Condition number 3. Here you need to check f of a equal to f of b or not. A is 0, b is pi. F of 0. That means sin 0 by e power 0. One most important point you need to remember, sin 0 is 0 and sin any pi is 0. Sin 0 is 0. 0 by anything 0. That means f of 0 is 0. Similarly, f of pi. Just now I said sin pi by e power pi. Sin pi is 0. 0 by anything 0. That's why 0. Now f of 0 and f of pi are equal. What it means? F satisfies condition 1, condition 2, condition 3 of Rolle's theorem. That is, F satisfies all the 3 conditions of Rolle's theorem. All the 3 conditions of Rolle's theorem. Then what happens, ma? What Rolle's theorem says? If a function satisfies all the 3 conditions, there exists C in open interval a comma b. Here a comma b is 0 comma pi, such that f dash of C equal to 0. Now we are going to check whether there exists C in between 0 comma pi if f dash of C equal to 0. For that, first find out f dash of x. F of x is e power minus x into sin x, ma. Here, to find f dash of x, you need to apply UV rule in differentiation. Differentiation of UV is UV dash plus VU dash. That means you should know what is differentiation of sin x, differentiation of e power minus x. You all know that differentiation of sin x is d by dx of sin x is cos x, d by dx of e power minus x is minus e power minus x. If you know that 2 formulas, you can e power minus x into differentiation of sin x cos x plus sin x into differentiation of e power minus x minus e power minus x. Now what you can take it as common, ma? E power minus x, if you take common, you will get cos x minus sin x. Now f dash of C 0 means e power minus c into cos c minus sin c equal to 0. When e power minus c 0, ma, this means e power minus c 0 or cos c minus sin c 0. When e power minus c 0, whenever in the place of c if you have infinity, e power minus infinity. So that cannot be in the given interval. So you cannot take e power minus c 0 as solution. Now cos c minus sin c 0, cos c equal to sin c. When cos and sin equal, you know very well, cos 45 is 1 by root 2, sin 45 is 1 by root 2. What it means? Whenever cos and sin are equal, their angle is 45 degrees. So here she should be 45. 45 in radians we can write like this. So 45 degrees is C value. Our interval is 0 to pi, 0 to 180. Can 45 exist in between 0 to 180? Yes, absolutely. 45 degrees is in between 0 comma pi. So hence Rolle's theorem is verified. Rolle's theorem is verified. Like this, one can easily verify Rolle's theorem for the given function. This is the way to check when function satisfies 3 conditions. Like this, you need to check continuity, differentiability, f of a equal to f of b. Then there exists C means there may be n number of c's after solving f dash of c equal to 0. There exists means at least one c value should be lies between 0 comma pi. Here also you got 2 c values. One is infinity, which is not lies between 0 comma pi. You can neglect that one. Next, c value is 45 degrees. That is lies between 0, pi. So Rolle's theorem is verified. Rolle's theorem is verified. So next problem, verify Rolle's theorem for f of x equal to log x square plus ab by x into a plus b. First, I am rearranging given function like this by using logarithmic rule. You know, log a by b is log a minus log b. Log a by b, log a, log x square plus ab minus log x into a plus b. Again, it can be splitted like this, log x square plus ab minus log ab formula is log a plus log b. That is log a log x plus minus into plus minus log a plus b. So this is actual f of x. If you split like that, then it is easy to find the derivatives. That's why. Next, as I said in the starting, properties of continuous and differentiable functions, a function which is defined in the interval a comma b are always continuous and derivable. Definitely it should be continuous. Now if you want, you can check. If you write in the place of x a or b, you won't get infinity. It is clear, or you can remember like this: the functions which are defined in closed interval a comma b are always assumed as continuous and derivable, otherwise we cannot do any further applications. That is one reason. So f is continuous in closed interval a comma b. So for checking f dash of x also, if you have any doubt, you can check f dash of x exists in a comma b or not. F dash of x I am finding. Differentiation of log x, you all know, differentiation of log x is 1 by x. Differentiation of x square is 2x. Differentiation of x is 1. If you don't have x in a term that is treated as constant, differentiation of constant is 0. Now, differentiation of log x, 1 by x square plus ab. Now differentiate again this term, differentiation of x square, 2x. Here you don't have x, differentiation of constant 0. Minus differentiation of log x, 1 by x. Do you have x in this one? No. Differentiation of constant 0. If you take x into x square plus ab as LCM, you need to multiply this one with this one. 2x into x, 2x square, minus this one you need to write here. 2x square minus x square minus ab. 2x square minus x square, 1x square. That means after simplifying you will get like this. But here in the denominator, if there is any case of getting 0, then f dash of x does not exist. But here you are having square and plus term and a into b. So there is no case of getting 0 in denominator. That means this one is exist in open interval a comma b. What it means? F is derivable. F is derivable in open interval a comma b. Next we need to check third condition of Rolle's theorem. Third condition, what it says? F of a. Write in the place of x a square plus ab by, right here a into a square plus ab. Again same you will get in denominator. If you write in the place of x a into a square, a into b, ab, both are equal. What you will get? Log is there, log is there. So both get cancelled. What you will get? Log 1 is 0. Now similarly find out f of b. F of b also, write in the place of xb, what you will get? B square plus ab. In the denominator if you write b into b square, b into a, ab. B square plus ab, again you will get. Both can get cancelled. Log 1 equal to 0. What it means? F satisfies third condition also. That means F satisfies all the conditions of Rolle's theorem. All the conditions of Rolle's theorem. Then what happens? There exists C in open interval a comma b such that f dash of c equal to 0. Now we will check if f dash of c equal to 0, then exists c in between a comma b or not. F dash of c equal to 0 writing is easy for this problem because already I evaluated f dash of x. In this, write in the place of xc. In this, write in the place of xc. C square minus ab by c into c square plus ab equal to 0. In this, write in the place of xc. Now send this term to right side, that becomes 0. Then what you will have? C square minus AB 0. C square equal to AB. C equal to root AB. If you want, you can check root AB always lies between A comma B. So Rolle's theorem is verified. Rolle's theorem is verified for the given function. We need to show that C exists in between AB, that we show. Okay, clear ma? Now, the next one we have to verify Rolle's theorem for this function f of x equal to x square minus 2x minus 3 in minus 1 comma 3. So clearly here f of x is polynomial. F of x is polynomial. That means it is continuous. Polynomials are always continuous and derivable. I said continuous in closed interval minus 1 comma 3 and derivable in open interval minus 1 comma 3. Next, third condition we need to check f of minus 1. If you write in the place of f minus 1, in the place of x minus 1, 1 plus 2 minus 3, what you will get 3 minus 3, 0. Similarly, f of 3, 3 square 9, 2 3s are 6, minus 3. This one also 9 minus 9, 0. F of minus 1 equal to f of 3. What it means? F satisfies all the three conditions of Rolle's theorem. All the three conditions of Rolle's theorem. Then what happens, Then there exists C in open interval A comma B. What is A here? Minus 1 comma 3, such that f dash of C should be 0. That means f dash of C we need to evaluate. F of x is x square minus 2x minus 3. F dash of x means differentiate this one, nothing just now I said differentiation of x square is 2x. Differentiation of x square is 2x. Differentiation of x is 1, 2. Differentiation of constant 0. That means f dash of x is this one. Now f dash of c equal to 0 means 2c minus 2 equal to 0, c equal to 1. 2c equal to 2, c equal to 2 by 1. So which lies between minus 1 comma 3. That's what we need to prove. Hence Rolle's theorem is verified. Rolle's theorem is verified. Clear na? Okay, like this one can easily evaluate Rolle's theorem if it is a polynomial. Very clear. Next we need to verify Rolle's theorem for x minus a whole power n, x minus b whole power n, where m comma n are positive integers. Whenever if you have x power positive integer, then we can treat that one as a polynomial. What it means? He is saying indirectly f of x is polynomial. When f of x is polynomial, we say that function is continuous. Clearly continuous in closed interval a comma b. If you want, you can check f dash of x f dash of x. For that you need f of x. I am writing f of x first. F of x equal to x minus a whole power m, x minus b whole power n. if you find f dash of x here, at the end while substituting f dash of c will be easy. And whenever if you want to check differentiability, you have to evaluate f dash of x. Now, UV rule, f dash of x needed, you know UV, u differentiation of v plus v differentiation of u. U differentiation of v plus v differentiation of u. For that, you need to recall one famous differentiation formula, d by dx of x power n is n into x power n minus 1. That formula only I am going to use. X minus b whole to the power of m, differentiation of x minus b whole power n, n into x minus b whole power n minus 1, using this, plus x minus b whole power n into differentiation of this one, m into x minus b whole power m minus 1. Now, you can take x minus b whole to the power of m minus 1 and x minus a whole to the power of x minus a, right? This is x minus a whole power m. So here x minus a. So you can take x minus a whole power m minus 1 and x minus b whole to the power of n minus 1 as common, so that you can simplify very easily. So here x minus a whole power, x minus b whole power n minus 1 common, but you are having here x minus a whole power m only. To get x minus a whole power m minus 1, after multiplying this one, this can be written like this, x minus a into n. Now multiply one. If you multiply this one with this, x minus a whole power m minus 1, here power 1, minus 1 plus 1 get cancelled, you will get x minus a whole power m only. What I am saying, this can be written as x minus a whole power m minus 1 into x minus a whole power 1. So m minus 1 plus 1 get cancelled, you will have x minus a whole power m only. Now I took x minus a whole power m minus 1 common, you will have x minus a. Here x minus a whole power m minus 1 common. Like this can be written as x minus b whole power n minus 1 into x minus b whole power 1. This is common. These two terms are common. What is left over? M into x minus b. So if you simplify these two terms, x minus a whole power m minus 1, x minus b whole power n minus 1, if you multiply, what you will get? Nx minus an, mx minus bm. Then if you take x terms common, what you will get? M plus n into x minus na minus mb. So take minus common, na plus mb will be there. Simply multiply, nothing. N into x, m into x. From that two terms I took x common, m plus n into x. N into a, m into b. From that two terms I took, the two terms I written here by taking minus common. Now this is f dash of x, which is exist clearly in open interval a comma b. Therefore f is derivable in open interval a comma b. Next, we need to check third condition, f of a. Clearly ma, if you write in the place of x a minus a, 0 into anything 0. Similarly f of b, write in the place of x b ma, b minus b here, write in the place of x b, b minus b 0. So 0 into anything again 0. That means f of a equal to f of b. What it means? F satisfies all the conditions of Rolle's theorem. Then what happens ma? There exists C in open interval a comma b such that f dash of c equal to 0. Now writing f dash of c is very easy because already we calculated f dash of x here. So in this, write in the place of x c ma, if you write in the place of x c, c minus a whole power m minus 1 into c minus d whole power n minus 1, here m plus n into c minus of na plus mb. Here I written in the place of xc, nothing more. Now if you send this term to right side, that becomes 0. That means m plus n into c minus na plus mb equal to 0. Send this term to right side, then what happens? C equal to, if you send first this one to that side, na plus mb. Next send this term to this side. Here m plus n is multiplying. If you take this m plus n to this side, that will divide. If you want, you can give some values for mn and ab ma. Definitely that value should be lies between a comma b. For different values of ab, if you want, you can check any value will have a value in between a and b. So Rolle's theorem is verified. Rolle's theorem is verified. So that is about Rolle's theorem. Like this you can solve in a number of problems in Rolle's theorem by remembering the shortcuts which I said to check a function is continuous or derivable. If you use that shortcut, you can easily check whether function is continuous or derivable. Basing on that, one can easily check the Rolle's theorem for given function. Are you clear, ma? Okay? Clear about Rolle's theorem?